Forget simply pushing against something. Rockets work because of the fundamental principle of conservation of momentum. This means, in a closed system like a rocket in space, the total momentum stays constant. The rocket ejects mass at high speed in one direction, and in return, it gains momentum in the opposite direction. This is how rockets move even in the vacuum of space. Conservation of momentum is the core principle behind rocket propulsion. The total momentum of an isolated system remains constant, meaning when a rocket expels propellant, it gains an equal but opposite momentum. In this diagram, at time t, the rocket has mass m and velocity v. As it expels a small amount of propellant dm at exhaust velocity ve, the rocket's mass decreases to m minus dm, and its velocity increases to v plus dv. This momentum exchange can be expressed mathematically as d times mv equals negative v times dm, where dm is the expelled propellant mass and ve its exhaust velocity. The rocket gains momentum in the upward direction, while the exhaust is pushed downward, driving the rocket forward through this equal and opposite reaction. This principle, governed by Newton's laws, explains why rockets work in the vacuum of space where there's no air to push against, unlike jet engines. Exhaust velocity, denoted as VE, is the speed at which a rocket expels its propellant. This parameter is crucial for rocket efficiency because it directly determines how much velocity change, or delta V, the rocket can achieve for a given amount of propellant. The higher the exhaust velocity, the more efficient the propulsion system. The relationship is captured by the rocket equation. Delta V equals VE times the natural logarithm of the initial mass over the final mass. This shows why conserving propellant mass is so important for achieving higher speeds. In a chemical rocket, the combustion process creates hot gases that are accelerated through the nozzle, reaching exhaust velocities between 2,500 and 4,000 meters per second. Advanced technologies like ion thrusters use electric fields to accelerate ions, achieving much higher exhaust velocities from 20,000 to 50,000 meters per second, though with lower thrust. This higher efficiency allows ion thrusters to accumulate significant delta V over time, making them ideal for deep space missions where propellant conservation is critical. The rocket equation is fundamental to understanding rocket performance. It shows how a rocket's change in velocity depends on its exhaust velocity and mass ratio. The equation is delta V equals exhaust velocity times the natural log of the initial mass over final mass. Here, delta V is the change in velocity, VE is exhaust velocity, m0 is the initial mass, and mf is the final mass. A higher exhaust velocity or lower mass ratio enables greater velocity changes. The mass ratio reveals how much propellant is needed, explaining why most of a rocket's mass must be fuel. Increasing exhaust velocity directly increases the rocket's velocity change. This is why advanced propulsion systems aim for higher VE values. The rocket equation quantifies performance and shows the critical role of propellant mass in achieving orbital velocities or interplanetary travel. SpaceX's Falcon 9 rocket perfectly illustrates momentum conservation in action. This reusable rocket expels approximately 400 tons of propellant at an exhaust velocity of about 3,000 meters per second, achieving a delta V of around 9,000 meters per second for orbital insertion. NASA's Space Launch System, or SLS, showcases the importance of high exhaust velocity in achieving the necessary delta V for lunar missions. With an exhaust velocity around 3,800 meters per second, the SLS can perform the velocity changes required to reach and insert into lunar orbit. However, rocket propulsion's reliance on momentum conservation also reveals its sensitivity. A 2024 SLS mission failure due to thrust asymmetry demonstrated how even slight imbalances in momentum exchange can lead to mission-critical issues, emphasizing the precision required in rocket design. The future of rocketry emphasizes efficiency and sustainability. Reusable rockets optimize momentum exchange to dramatically reduce launch costs, while electric propulsion's high exhaust velocities make it essential for deep space missions. Reusable rockets, pioneered by SpaceX, allow boosters to be recovered and reflown multiple times. This optimizes momentum exchange by reusing the same hardware, cutting costs dramatically. For example, the Falcon 9 has reduced launch costs by 80% since 2020, with per kilogram costs now at just $500 to $1,000. Electric propulsion systems, such as ion thrusters, achieve extremely high exhaust velocities compared to chemical rockets. While chemical rockets reach about 3,800 meters per second, ion thrusters can expel propellant at speeds up to 50,000 meters per second. This high efficiency makes them ideal for deep space missions where thrust is less critical than sustained momentum change. NASA's Psyche mission exemplifies electric propulsion's potential. Launched in 2022, it uses ion thrusters to slowly but efficiently build up velocity for its journey to the Psyche asteroid, arriving in 2029. This demonstrates how high exhaust velocity enables long-duration, low-thrust deep space exploration. Looking ahead, hybrid chemical electric systems and AI-driven optimizations promise even greater efficiency. These advancements will continue to leverage momentum conservation for sustainable and cost-effective space exploration. Nuclear thermal propulsion, or NTP, is an emerging technology that could revolutionize space travel. Unlike chemical rockets that burn fuel, NTP uses nuclear reactions to heat propellant gas to extremely high temperatures. DARPA's Draco program recently demonstrated this technology, achieving exhaust velocities up to 8,000 meters per second. This is more than double the speed of traditional chemical rockets. With such high exhaust velocities, NTP could significantly reduce travel times for missions to Mars, potentially cutting them in half compared to chemical propulsion systems. However, despite these promising advances, regulatory hurdles still remain, including safety concerns and international agreements governing nuclear technology in space. In this final section, we'll summarize the key takeaways from our exploration of rocket propulsion and look ahead to the future of space travel. Rockets fundamentally operate through the conservation of momentum, where the expulsion of mass at high speed propels the vehicle in the opposite direction. The exhaust velocity, or VA, determines how efficiently this momentum is used. Key trends shaping the future include reusability, which has dramatically reduced launch costs, electric propulsion for efficient deep space missions, and nuclear thermal propulsion for faster interplanetary journeys. As SpaceX CEO Elon Musk stated in 2025, rockets are essentially momentum machines, making interplanetary travel feasible without relying on external forces. Looking ahead, we can expect massive growth in the space industry by 2030, with innovations in propulsion technology enabling more ambitious missions and sustainable space exploration.